Assalamu alaikum, dear student. I hope you are fine and doing well. Today our lecture is about RSA cryptosystem. This is the first crypto system of public key cryptography, which was developed by Ravizit Shamir Edelman in 1977. Uh, this is quite famous crypto system that is based on IFP problem, integer factorization problem. So largely we have discussed two basic problems of a public key crypto system. One is integer factorization problem and second one is discrete log based problem. Today we will formally develop this RSA crypto system, how the integer factorization problem, means to say any non-zero composite number can be decomposed into a product of prime, how this concept will evolve around RSA crypto system. So let us come up with some objective of today class. So today we will discuss some historical introduction of RSA and the procedure involved in RSA and some trivial example of RSA. And then we will end up with the correctness proof of RSA, why this RSA crypto system work and why we are going this encryption as well as decryption function are basically inverse of each other, and so that we will get back our plain text. So this is what you call the correctness proof of RSA. And dear student, you must keep one thing in your mind whenever you are developing any public key crypto system. The correctness proof is one of the and necessary and sufficient step towards designing any public key crypto system. If you are unable to provide the correctness proof of your crypto system, then in that case you can say you cannot encrypt your message, but unfortunately you are unable to decrypt your what you call the ciphertext. So in that case, the correctness proof is one of the necessary step in any public key crypto system. So these are three cryptographer that basically developed. This is the name of this scientist is Ravizit, as I place it over here, Shamir and Edelman. They basically developed this crypto system in 1977, and this crypto system is fundamentally based on number theory, or so that is why I have give you some lecture on number theory. RSA is fundamentally based on integer factorization based problem, like so. Let me tell you. So this is a integer factorization based problem. So you have one, two very large prime number, and you can multiply them very easily, but you cannot get from a very large number, composite number. You cannot. It is quite difficult to factor this product. Means to say, get back your prime from this product. The public and private key in RSA is based on very large prime number, and also the algorithm is simple, but complexity lies in the selection and generation of public and private key. So there are fundamentally three basic steps in any public key crypto system. One is key generation, and second one is the encryption algorithm. Third one is decryption algorithm. I mean to say there are three components: key generation algorithm, encryption algorithm, and then you can say the decryption algorithm. In that case, if you can see over here, though I told you the key generation algorithm. So the key generation algorithm include the step that you have to choose very two distinct prime number, then compute their product, and n is the modulus for the both public and private key. So another one is you have to compute the Euler phi function, which is p minus 1 q minus 1, or it can be written as n minus p plus 1 minus, like, and choose a one integer between 1 to phi of n, where GCD with the e is 1. It means to say e and phi are co-prime. And e is released as a public key exponent, or you can say encryption exponent. And moreover, to determine d, which is the inverse of e under mod phi of n, d is the multiplicative inverse of e under mod phi. So you have to, it means if you multiply e and d, these are congruent to 1 mod phi of n. In that case, d is basically the private key, which will be utilized in case of decryption. So encryption is a function that basically convert your plain text into a ciphertext. So in that case, the encryption is, you can say, cipher is equivalent to p to the power e, where p is plain text and e is the your public key. And the one thing you must keep in your mind that the honor of the public as well as private keys is receiver. And uh, and uh, and uh, for decrypting, you can just take c to the power d, you will get back your plain text, and which is basically your original message. So requirement for RSA is it is possible to find E, D, and inside that M to the power E into D mod n is M. You will means to say if you take M to plain text to the power E and then plain text to the power D, you will get back M, where M is less than N. It is relatively easy to compute M mod P and M mod D for all N where M is less than N. And it means it is infeasible to determine D and E uh, and quite easily. So complexity of RSA, basically, if you have like Alice have plain text and she encrypt your plain text with the help of Bob public key and send it via insecure line of communication. The if will have to recover it, but by recovering plain text from this what you call expression, you need c to the power e, uh, e power of c, which is involve exponential complexity. It means it is quite hard problem for Eve to determine plain text from this exponent for a very very large number of n. So in that case, here the polynomial complexity involved and receiving, and is also involved polynomial complexity, because some trapdoor information is available with Bob as well as Alice, and moreover for Bob Bob has some trapdoor information. For them, for Alice and Bob, the problem at both of the end, means to say at the end of Alice as well as at the end of Bob, the complexity of this at the sender as well as receiver end is polynomial time, but for E it is an exponential time. So how it will work, procedure for this is, uh, basically Bob will if you just multiply two prime numbers, and these prime numbers are secret, and the secret are basically selected by Bob from receiving end. So ultimately Bob will generate the public. This is the basically the key generation algorithm, that Bob will select one unit element group with multiplication and select P and Q and multiply them, and he will get N, which is public, and P and Q are private. So select E and D, and D is a private, and he kept D as a private and send the E and N to Alice, and these are basically through some secure channel. He send this public key to Alice, and Alice will use this public key to what he call encrypt any plain text by and here if you can see over here the encryption procedure involve ring ZN uh, as well as decryption also involve ring but while calculating your key generation algorithm in key generation algorithm we involve unit element of that ring. Basically, that ring means I mean to say here we have involved unit element. So there are two types of structure that were involved in RSA. One is under mod 5 of static and another one is ZN. So here this is a ring structure and this is a cyclic group structure of unit element. So if you can look over here, the Bob will what you call select to P and Q and publish N. Means to say publicly announce this is N. So phi of N we understand publish E and compute D inverse of E in phi of Z and hence E into D is counted to one mod N and D is a private key. And what actually Bob will do. So Bob will take value P and Q and multiply these two very large prime and calculate its D and share publicly N as well as E and send it to publish key, use it to basically Alice will use this information to send a message to Bob. So this is whole mechanism and why he announced publicly this what you call this information. But Bob will not announce this information as a public. But this will be a public and this is a private one. So this is again, you can say some pictorial diagram to understand what does actually it means. So message is M and what Alice will announce N and E as a public and then what actually the Alice will do. Here the M is the message and this message is encrypted by this guy from sending it and he used this public key, public information M to the power E where M is in plain text mode N and send it to what you call receiver and receiver will use his private key which is D M to the power D and in that case she will get message M. So this is the whole story of RSA. So as I told you, RSA basically deal with two structure. One is ring structure and the second one is group structure. This is group structure and the key generation is based on group structure and the encryption and decryption is based on ring structure. I mean to say element of encryption and decryption will be from ring and element of key generation will be from group structure like unit element. This is random pseudo code for RSA key generation. You have to see it, and this is for decryption. So let us take one very trivial and small example that will help you to understand what does how your RSA will work. Bob will choose P and Q. Since I told you P and Q is the secret information, secret, and that the honor of basically the key are uh, receiver or means to say Bob. So he will calculate product of P and Q 77, and then he will calculate phi of n, which is 6. No, choose to exponent E and D mod 5 of 6 is static. If we choose E to be 13, then D is 37 under mod. It means E into D mod 60 is congruent to 1 mod 5 of n. So say our plain text is 5. So we'll calculate Sapphire. Sapphire is equal to 15 to the power 13 mod 77 is 26. So plain text is 26 to the power d, which d is 37. Mod 77 is 5. In that case, you can see over here, our ring is basically Z77, but our some groups such as Z60 steric means to say it has basically 60 element whose multiplicative inverses are possible. So there are basically two structures. Another example, no, assume another person, John, wants to send a message to Bob, and John used same public key announced by Bob. So the public key 63 mod 77 is 21, and P28 to this and mod. We will get back 63. Another very simple example. So take two very large prime like P and Q and multiply it. So you will get 15 91 1 lakh 59,197 as a n, and 5 of n is 1 lakh 58,400 as a 5 of n. It means there are 1 lakh 58,400 unit element in this ring. So E is this one and D is this one. So in that case, if you can see, suppose Ted wants to send a message note to Jennifer, then he changes each character to number from 0 to 25 with each character coded as 2 digits. Then he concatenate the two, like if I can demonstrate this with the help of this one, like this one. So if you have no side, n is 33 and no is 14. So concatenate both numbers. So p to the power this one, 343 mod this one, and you will get sample text this, and p uh, this is p, you will get p 33 67 7 to the power this one, 12007 mod n. So you will get p like this one. So through concatenation, if your mod are very large, in that case you will just concatenate the two numbers, like n is mapped to in under modulo 26, n is mapped to 30, and O is mapped over 14. So in that case, you just concatenate the plain text. Instead, you are dealing with individual element, like you apply RSA on n individually, and then apply RSA individually on O. Instead of that, you will have to concatenate both and apply both on combinedly apply this RSA on this plain text, like 13 and 15. So this is another trivial example you have to see. So this is not X, this is multiplication. So dear student, you have to take it as a homework. Then another example, what I basically clarify from this example, that your message can be of form binary. So if your message is in form of binary, so you have to convert this first from binary to integer or decimal. So for that, after converting from uh, binary to decimal, then you will have to apply RSA, and rest of the procedure is same. These are some Potential attack on RSA, factorization attack, chosen ciphertext, encryption exponent, decryption exponent, plain text, modulus, and implementation. So factorization attack is that if your n is very small, then in that case you can get p and q. Their factors are quite easy to. It is if n is quite small, then it can easily be factored out into the product of prime. So Eve can get chosen ciphertext. It means Eve can get the cipher for some chosen plain text or exponent. I miss to say, if you have n is very so from this you can say the exponent. You can get exponent as well as decryption exponent. But if your n is small. Similarly, if you can take a short message and cycle it and unconceal, and in that case, there's another non-plain text attack. So these other are related with the implementation. So I'm not going into the depth of this attack. So it is again what you call the optimal asymmetric encryption padding. So it means to say how you can pad some bits into your message bits and how you can use your RSA or any encryption public key crypto system to some what you call thresholding symmetric key crypto system, or you can say how you can implement to some specific number of bits to apply your crypto system to some specific number of bits, or to add some bit into your original message and then encrypt your what you call the message. So this is one of the optimal asymmetric or padding based symmetric key crypto system. So this is here you can see over here we take very large P and Q. So corresponding basically P is 159 digit number, and Q is again what we call the 159 digit, and choose a 512 bit P and Q. So in that case, E then we will calculate n phi of n and then choose E and test relative primeness with phi of n. It's a quite difficult problem. If you can look over here, so the P is 309 digit. So phi of n is also 309 digits. If you can look over here, if you can count it, so there it will be 309 digits. So if you can take E 35,503 535. The ideal is 65 537. So in that case, E is this one. So the D, which is inverse of E to mod phi of n. So here you can see over here, this is a very large number. So it's quite impossible to decode it. So if you have prime like this one, this is a test. So T is 19, and then space is 0. Then I is 7, and then S is what you call just space. So this is what you call the so this is one of the message like this one. This is one of the message Alice want to send it to Bob. So C to the power E, which is like this one, cipher to the mod for n. So the cipher is very large. So in that case, if Bob want to recover the plain text, so he will take C to the power D. That is this one, like C to the power D mod n, in that case he will get this message, which is the plain text. This is a test after decoding. So this is just a mapping. Mm, So the correctness proof. Dear student, before starting with the correctness proof, let us take one very simple result to understand what does it means and how it will help you out in while taking proof of RSA. Why RSA is encrypting as well as decrypting. So let m be a positive integer. The integer a and b are congruent mod m if and only if there is an integer k such that a equal to b plus k times m. Say I'm saying that a is congruent to mod 3, mod m. That is a is congruent to mod m. If and only if a is a can be written as b plus k times m. That is 4 is congruent to 2 mod 2. I mean to say when you divided 2 by 2, the remainder is same as if you divide 4 by 2. So in that case, dear student, 4 is written as 2 plus 1 time 2. Or can this is congruent, and the how the congruent will convert it from congruent will convert it from congruent is converted to equal. So there is a difference. If you can say the congruent, two numbers are congruent, but they are not equal. But how your congruency classes will convert it from congruent to equivalence. So equal now. How two numbers which are congruent, how the equality prevail between them. So if 2 is congruent to 2 mod 2, this if and only if 4 is equal to 2 plus 1 time 2. So in that case, let us, we have C is congruent to M to the power E mod M. This is basically encryption algorithm. Why, if you can take C to the power D is congruent to mod, is congruent to M mod N. Why this is always give you the plain text. If you can take C to the power D and C is M to the power E, so, so in that case, M E to the power D mod N. If you can see, E and D are basically inverse of each other under mod phi of n. That is, E into D is congruent to 1 mod phi of n. If and only if I am using this result. I'm using this result. This is E times D is equal to 1 plus H times phi of n. H, it may be H, it may be K, it may be any non-zero positive number. So in that case, if you can see over here, dear student, I'm just taking this power. E into D is congruent to 1 mod K, where K is phi of n basically. So in that case, ED is equal to 1 plus H time phi of n. So I just place this one on to the left side of this equality. So my result will be ED minus 1 equal to H time phi of n. Like ED minus 1 time H of phi of n, where phi of n is this one. So I am now utilizing this ED is equal to H time phi of 1 phi of n, with where phi of n is p minus 1, q minus 1. So, dear student, if you can see over here, so this will be Basically, I'm using this one. ED is 1 time phi of h time phi of n. So one power will be like this one, and if you add this both power, you will get and this get you will get this one. So uh, ED is equivalent to, basically the ED is equivalent to 1 plus h time phi of n. So you just take this to the power of m. ED is equivalent to 1 plus h time phi of n. So uh, h time phi of n is like this result, and m to the power 1 is this one. So if you can look over here, I just take out this h outside from this, like m to the power p minus 1 to the power h time q minus 1. I can write it like that. If you can just multiply this expression again, you will get back this. So, dear student, if you can m to the power p minus 1, then h to the power p minus 1. So, this result is what you call the Fermat-Little theorem. So, m to the power p minus 1 is what under mod p. It is always 1 by Fermat-Little theorem. So in that case, this will be 1. So 1 to the power h time q minus 1 is again 1. So you're left with m. So it means if you can take c to the power d, m to the power ed is counted to m mod n. So you'll get m. In that case, you can say if you decipher your ciphertext, so you will get back your plain text. This is one of the correctness proof of RSA, and this will be quite important for any public key. Correctness proof is one of the fundamental steps while devising any crypto system. These are some references which I have followed while preparing this lecture. Uh, I hope you enjoy. Please stay at home. May Allah bless you all. If you have any question, do ask me. Till then, Allah Hafiz.